So this is looking at communication channels, the data link layer from the OSI 7 layer model. In this case, we're looking at reliable communication or transmission of data between two nodes. Now these two nodes could be a computer, a hub, a switch, or even a router. The router belongs to layer 3 in the network, but I've included it here just for completeness. Now, this data link layer can actually be broken into two subparts. The first is the medium access control, and the second is the logical link control. Both those layers are responsible for different things, and I'm going to cover them now. So, the medium access control is responsible for how networks gain access to the medium, i.e. what they're transmitting on, wires, radio waves, etc., and when they have permission to transmit data. So I've included a couple of schemas here. The first is Aloha from the University of Hawaii, henceforth the name. But basically, you speak when you need to. And the problem with that, of course, is everybody speaks at once. You have this overlapping of data and things get totally garbled and nobody knows what's going on. So the first, I suppose, adaptation of that was what they call slotted Aloha, where everybody has a time slots where people can speak, but you can only speak in the time slot. And as a result, it's fixed some of the problems, but if two people speak at the same time in that same slot, then again, data gets lost. So, carrier sense with model access was developed. And I am skipping a few stages in between, but just covering some of the important highlights. Basically, it waits for silence before speaking. So it waits for a gap in the conversation. Then you have carrier sense model access with collision detection. So it waits like the previous version. However, if someone else starts talking, it stops. So that's to minimize loss of data. And then, of course, everything gets worked out from that point onwards. Now, if we dive into the transmission modes that exist on these communication channels, the first is simplex. It's one-way communication only. So the example is the school's PA system or public address system. Radio, television, or even YouTube are great examples of this as well. Next up, we have half duplex. So this allows two-way communication, but only one direction at a time. So you've got things like walkie-talkies where you press the button to speak, and push to talk in Discord, same sort of thing. Then we have full duplex as a transmission mode. This allows two-way communication at the same time. So we have not talk phones, but telephones, and mobile phones as examples, and any sort of voice over IP technology such as Discord and the countless others that seem to exist. Now, how that communication happens is also an important idea. Whether or not the communications are synced or synchronous versus asynchronous. So the critical point here is whether or not they lock into that same rhythm to do their communication. So that covers the communication channel, and now we move on to the logical link control. So if the MAC was when you should speak, the logical link control is the language you should talk with when speaking, similar to network protocols, or a form of network protocol in this case. So these link protocols cover the IEEE 802 standard used for local area networks, metropolitan area networks, Ethernet, and even wireless LAN. The PPP protocol used by point-to-point protocol used by modems, old style communication. And finally, cellular systems such as used for the mobile phone. Another critical part of the LLC is making sure that that message has been understood, that the communication has got through and it's free of errors. So the first example of this form of error checking was the parity bit. So if you look over here on the right-hand side, we have a single block of data of 7 bits. This conforms to the old ASCII standard, the American Standard for Character Information Interchange. And on the end of it, we've tacked on this additional bit, depending on whether you go for even or odd parity. And at the start of the message, they'll be saying, hey, we're using even parity this time, or we're using odd parity this time, whichever. And this is great. If you get a single bit that gets flipped because of miscommunication being too low or too high because it's just got pushed too far, then you go, oh wait, that's a mistake. I don't know which bit it is, but we'll fix it. And that block of data would get resent. However, there's a small problem with this. If you have 2 bits that are flipped, all of a sudden it still has even or odd parity, but the message is wrong. So what has been done in the past is another block of data is added down the bottom. So an eighth block of data, which is basically just a check on all the columns here to make sure that they all conform. And that way, it's unlikely that the data will get sufficiently garbled and still appear correct. These days, there are more complicated forms of error checking. The primary one is cyclic redundancy checking, and this is commonly used throughout digital networks. There are a huge amount of standards. They're all different forms of hash functions. So if you're doing software development or other more complicated computing topics, then the hash function, this is an example of a hash function. Another example of the hash function is the MD5 algorithm. So this was originally used in cryptography but had lots of vulnerabilities for it. But basically you give it a stream of data, ones and zeros, and it produces a 128-bit hash value. You'll see this pop up on when downloading software, if you actually download your own software, as a checksum to basically verify the integrity of that data, that it hasn't become inadvertently corrupted. Another one is the SHA-256 algorithm, which again a different standard, but the same basic idea. And that sort of wraps up this with a little bit of a step sideways into hash functions.